Next, we're going to look at the forward Euler method for solving first-order differential equations. For the forward Euler method, we replace the derivative, say, dy dt with y t plus h minus y of t divided by h. Again, in this case where h is the step size or increment size, or if we have the case where maybe the independent variable is x. If the independent variable is x, we might have something like this. Same idea. In most examples that I'll go through, t will be our independent variable, but it doesn't really matter. The process is the same no matter what. So let's look at an example. Just take a look at this example. We're going to solve this first order ordinary differential equation. It has an initial condition of y equals 0. This will be at time t equals 0. And we want to solve it on the interval t equals 0 to t equal 1 using Euler's method with a step size of 0.2. Let's take a look at that. So obviously from the context, the independent variable is t, so this is going to be dy dt. But again, we're going to replace dy dt with y t plus h minus y of t divided by h. That's what we're estimating our derivative by this. Then on the right-hand side, we're going to have 3t square root of y of t minus 0.25 y of t, like this. Now notice when we set the equation up originally, the only term that will have a t plus h is going to be this this term right here, this over here. Everything else will be just a t. And so this side is going to be one step ahead of everything else. So let's solve for y of t plus h. So I multiplied the right-hand side by h, the denominator, multiplied the right-hand side by h here, and then added y of t to both sides, so we get this. So this is what we're going to use on every step to solve for the next point in our solution. So we're going to start with the starting point y0 over here, and then we're going to solve for y0 plus 0.2. Then we get that, we're going to solve for y0 plus. So we'll be going in increments, and we're going to start with the initial point, y0, we're given. We're going to put it over here and then solve in increments. So we're going to solve for the first one, which would be y of 0 plus 0.2. So that'll give us y 0.2. Then we're going to solve for y 0.4, then y 0.6. And we're going to use the information we got from the previous step to do that. So let's go ahead and do that. So we're going to use our equation here. We're given y of 0. That'll go over here. And then we're going to solve for y of 0.2, which is going to be 0 plus 0.2. So let's go ahead and solve that. And so let me now put the values in. So over here, this is going to be 0.2. And on the right-hand side, y of 0. And our increment size is 0.2. And then 3. And again, our starting initial value of t was 0. And then the square root of y of 0 minus 0.25 times y of 0. And so again, notice everything on the right-hand side is from the previous step, from the first step. And on the left, you're a step ahead. So let's now put the values in here. Y of 0 was given as 2. And again, here's going to be 2. Of course, that term's going to end up being 0. Like this. And this gives us 1.9. So now we can solve for the next one. Now we're going to find the next point. So again, we calculated 0.2 a few seconds ago. Now we're going to find 0.4. Remember, we're increasing by 0.2. And keep in mind, again, we've found 0.2 is 1.9. So keep in mind the equation we're using, which is right here. So y of 0.4, again, we're using this bottom equation, is equal to y of the previous step, 0.2. And then the increment size here is 0.2, 3. Again, notice we put everything on the right-hand side from the previous step of y 0.2. And the t was from 0.2. Of course, the increment, that's just a fixed 0.2. So now substitute everything. And when you put this into your calculator, you get 1.97. So let's now go to the next step, step 3. So for the next step, we're going to find y 0.6. Remember, we're always increasing it by our increment of 0.2 because we were just found y 0.4, which was 1.97. So let's go ahead and find this. So we're using our scheme here. Right here on the right-hand side, we have the previous step, 0.4. T was at 0.4 everywhere. In here, in here, in here. In the left-hand side, we have 0.6. Now we'll substitute the values into that. And so I substitute our values, 1.97, 1.97, 1.97, and put those all in. And that's going to give us 2.2, looks about 2.208 roughly. And so now let's go to the next step. Again, we're going to use what we just found. Again, keeping our scheme in mind, we want to solve for y of 0.8. On the left-hand side, we have that. And on the right-hand side, everything is from the previous step, 0.6, 0.6, 0.6. And of course, that was part of the equation, 0.6 for t. And so again, substitute all your values, y at 0.6, y at 0.6, y at 0.6, and t of 0.6. And when you put all this in your calculator, you get y of 0.8 of 2.6. I guess we round it to 2.633. Then use this to calculate your very last point. Remember, we're going from 0 to 1, so the next one will end up being our very last point. So we're going to find y 1.0, given our previous value we just calculated just now, 2.633. So that's going to be our step 5. So for step 5, we're doing the same stuff. Left-hand side is 1 increment higher than before. Right-hand side is the previous increment. Everything's at 0.8. Left-hand side at 0.1. Now substitute the values. Again, we found 0.8 a few seconds ago. And then substitute everything at 0.8. Again, we found that a little while ago. Substitute all your values in. Then when you put this in your calculator, you get around 3.280. And so that was the last point that we were supposed to find. Remember, we were supposed to go from 0 to 1 for our time increment. And we'll go in steps of 0.2. And so that's our answer. Sometimes we're interested in just the final answer at the end of the interval. Other times we're interested in all the points along the way. So if we needed all the points along the way, of course, the original one was was 2. And at time 0.2, we had 1.9. At 0.4, 1.97, 2.28. At 0.8, we had 2.633, and at 1, we had 3.28. So now we're going to put the same problem into Matlab. We're going to put this problem into Matlab. We already found our scheme here. Remember, we replaced the derivative with this, solve for y of t plus h. So now we're going to do Matlab. Now we're going to make the Matlab code, and I'm going to keep some space up here and below here. I'm going to fill things in, but this is going to be our equation. So what I did here, on the left-hand side, I'm replacing the t plus h with I plus 1. Right-hand side, everything's at I. Notice we also have to index the times t here. And I put the h in here. And this is the square root. You could also use that square root command that they have. I'm not sure what the difference is between those two. But let's do this. And then, so we're going to have like a loop, this being done iteratively. So, and t is going to have to be increased on every step. So that we're going to have some expression for that up here. So let's do I plus 1 is t. And we're going to start with our initial value and say times I times h. So we're going to start with our initial value here. And then every time we go through the iteration, it's going to increase. So it's going to start with the first value, whatever that first time value is. I think we're going to start at times 0, if we're starting at times 0. And then it's going to increase by h every time it goes through this loop. Oh, and by the way, as I probably mentioned previously, I always use I instead of I for my index, because often Matlab will interpret I or J, if they're by themselves, as a complex number. So I don't want to have that happen. So let's make our loop here for I equal 1. And I'm going to make a variable here. I'm going to call this variable max I. You can call this whatever you want, but that's going to be like the last increment. Like in the one we did by hand, we went through, I guess, 5 steps. And so so if we were going to use that increment of 0.2, you could just go ahead and set this at 5 steps if you wanted to. But I'm going to have it calculated each time. And I'll show you that here in a minute. And let me think if there's anything else needs to be within our for loop. And I don't think there does. So again, this is going to be the loop. It's going to calculate these points iteratively, like what we did by hand, except it's going to do it here. Then we're going to have our starting condition. So we're going to have our original y value and our original t value. So again, we were going from t equals 0 was our starting point. We're starting at t equals 0. So our t1 up here is going to be 0. And I'll put the semicolon here. In fact, you can put the semicolon on a lot of these at the end of a lot of these equation lines so that it doesn't print everything out. Then we said our initial condition was y of 2. Now, in this case, our initial point, we're going to call it I1, and that was 2. So this is going to be, let me put it here, this will be like, say, the initial condition, which we're going to start at 1. We're going to call it 1, though it's actually going to be starting at t equals 0. That's going to correspond to t equals 0. And also, let's decide, like again, the maximum, let me call this max. You can use whatever names you like. I use sometimes odd names. So this is going to be the maximum time value. And then let's also have an H in here somewhere. Now I'm going to have to make some more room here. So I had to erase everything, give myself more room on the paper here, because we're also going to need the increment size. Again, let me, for right now, set it at 0.2 the way we had it when we did it by hand. And so what I was doing over here, rather than having, say, the maximum value for our loop, we'll just calculate. We'll put in a little equation here to calculate what our maximum value for our loop is going to be. And we can just call this MAXII. And that's going to be our maximum, our max T minus our initial T value. I'll write it like that. And divide this by H. So that means, again, if we want to have a value of 0.2, then this is going to have to go through 1 minus 0 divided by 0.2. So it's going to have to go through 5 iterations. But so I don't want to enter this every time in case I change this. I'll just change my increment size, then it'll automatically fix this. So finally, let's plot our stuff here. Plot our T and Y. I'm using really the simplest commands right now. We can add things to them later. So that code right there should work. We're starting with our initial values here. We're starting at T1 is 0. Our initial Y value is 2, and our maximum value of T is 1. Increment size 0.2. Then it'll calculate the number of iterations that we have to do just using this simple calculation. And then this will increase the time step every time. So we're going to start with, say, tier 1, then keep adding an increment every time. Then we'll calculate our values and we'll plot this. So I put the Matlab code in just the way I had it here. I just added a couple things. At the beginning, I put a clear all. Now, Matlab will tell you that you don't need to do that, though. Sometimes if there's extraneous values in the environment, they'll get pulled into Matlab. So I like to put the clear all. Now, if you have that values for variables that you need to keep, maybe you're doing something else on some in Matlab, don't put the clear all in if you need to keep other variables. But if you can erase the variables, I put this in usually. So, and the other lines I put in just like I wrote them. And remember that Matlab is case sensitive. So when I ever put the max T, you have to do it the same everywhere. And I put all these in, put the loop in. I put just a couple of extra things here. I put a hold on here. And actually, I probably should put this maybe afterwards like this. So after the plot, I put a plot, and then I put the hold on and the grid on to make a nice grid. And so let's go ahead and calculate that. Of course, go up here to the editor, and then be sure you're an editor at the top. Then hit run, and it should give you a nice picture. And it'll give you a picture something like this. And so again, it plotted the points. In fact, we can check here, see that that it matches what we did when we calculated by hand. Check at 0.2. You'll put this at 0.4. We get 1.97. At 0.62, 0.209. At 0.8, we got 2.633. And then at 1.0, we got 3.281. And so that's our curve here from doing this in Matlab and putting that code in. Now, notice there's a couple of things here that I put in extra. You notice I have the x-axis marked and the y-axis marked, and I have a title at the top, and I'll show you how I put those in. So again, here's the code that we talked about. Then also I put some extra lines down here. Notice I marked the x-axis. I use this X label, and you can do this X label and write whatever you want on the x-axis. Now I changed the font size to 14, make it a little bit bigger. Though I ended up changing everything to the larger font size, so I'll show you that in a minute. And I put the title here, title differential equations. So in each of these, whether it be X label or the title, just put whatever you want on the axes. Just put it within quote marks. And if you want to change the font size, write font size, comma, whatever size you want here. Though what I did at the bottom here, I added these lines, which will change the font size, not only of the labels, but also of the numbers that are on the axis. I usually like to make them a little bit bigger. So I typed in this AX equals GCA, and then AX dot font size, AX dot font weight, and I made the font size 14 and the weight bold. That gave us the larger values. But you can experiment with that as you wish. Probably many of you know MATLAB much better than I do. You can add those features you want. But in any case, this is the code we did to solve our problem. Now, I should mention here, since we put the increment h into our MATLAB code just as h, we can change this to anything that we want. So we can make our increment much finer, and that will give us a more accurate answer. Again, we didn't want to make it too fine when we were doing this by hand, but now that we're using the MATLAB, we can make it as fine as we like. In fact, let me make this 0.001. And that's going to give us a much better answer. That's going to give us a much finer solution. In fact, we can even compare the solution, because I still have my graph up. So let me compare the solution. Also, what I'm going to do is I'm going to make this line a little bit different. In fact, I'm going to make our line width a little bit different so we can kind of distinguish it from the one that we already plotted. So the line that we plotted originally was a black line. So I'm going to make it into a red line. In fact, I'm going to make it dashed. So over here, I'm going to have the same plotting command we had before, except I'm going to make the line dashed and red. You do this by putting it in quotes and put the double dash R. And I'm going to make the line a little bit thicker. And so we'll plot this using this finer increment. Again, that'll automatically calculate the extra iterations that we have to calculate because we put that little command in here. So let's take a look at this. So when we did that, we get this red dashed line, and it's a much better solution, much more accurate. Notice it's a pretty big difference from the line we got before. Notice the line at the bottom there, the black line. It's there's a big difference between it and the red dotted line, the dashed line. And again, sometimes the correct solution might be lower than this rough estimate we had. Sometimes it's going to be larger. In this case, the more accurate estimate is larger, and so you can see the difference. But the main point is the way we wrote the code, you can change that increment to whatever you would like. And you can use the same type of scheme, just we did here, for any first order differential equation you want to do in Matlab. You can just use this here. And in another video, which I'll link below, I'll show how to use the solvers in Matlab to solve differential equations. So you don't have to use like a scheme like we did here. You can just use the solver. And also, later I'll put a video showing how to do second order differential equations using the Euler method.